This presentation is called Understand Electric Power from Digitized Electric Powertrain Data. So thanks very much for joining. So we will discuss electrification and the challenges of electrification, and more particularly, we'll focus on how digital signal processing in a post-acquisition phase in a software like ENCODE, Glyphworks, can help to enable the assessment of the dynamic power of all components and operating states to be analyzed, right? So we'll calculate power in the post-data acquisition phase, and we'll see that running it, post-data acquisition will allow us to run more complex analysis scenarios and go more in depth, in our analysis. So let's start. So first, a quick introduction on the efficiency of an electric vehicle powertrain. Then we'll quickly discuss the benefits of collecting high-speed digitized data. Then the benefits of performing offline data processing. So once you have the data in a file, and then we'll see a bit in practice, how do we calculate power efficiency and how do we get more insights from your test data. I'll end up with a live demo of the software with real data, and we'll have the Q&A session. So first, let me just introduce our company. So I work for Proinsia, which is part of HBK, and Proinsia helps engineers deliver durable and reliable products and avoid the cost of unexpected failures. To do so, we develop two software brands, the ENCODE brand for durability analysis and the ReliaSoft brand for reliability analysis. But we also provide training and education, right, courses and stuff. So on reliability, durability, fatigue theory, and the use of the software. We also have services. We've got a material testing laboratory in the UK, and we've got our solutions team to help you with asset management and design, development, and test. If I quickly give you an overview of our software portfolio, we have a number of well-known softwares. So if I start on the left-hand side here, we've got all the tools for reliability analysis under the ReliaSoft brand, right? So in the first column, you've got Wible++ for failure data analysis and failure and test planning, and we get like BlockSim for system modeling. In the next column, you've got all the tools for the reliability management. So you want to manage risks and maintenance, you want to manage actions. And then we move into the ENCODE columns. So the first of the ENCODE columns is about the desktop tools. So we get Design Life for CAE-based fatigue analysis. Glyphworks for test data analysis, general purpose test data analysis, and with a strong flavor for durability analysis, and Vibesys for the NVH type stuff, vibration and acoustics analysis, right? Then the last column, we've got the data management tools, and Akira, for instance, is a web portal to access the data and to access also those tools in a thin client fashion. Right. So we'll concentrate on this presentation on Glyphworks and also Vibesys when it comes to doing some frequency based analysis, right? So let's start with by looking at an electrical vehicle and its powertrain, basically, right? So it's here we have a DC battery, right? A battery. We have an inverter that turns the DC current into AC currents to supply the motor with some current, right? And the motor is producing some mechanical work, and that's the transmission here, and that allows the vehicle to move. So between the DC and AC, right? You've got the inverter that's turning DC current into AC current, right? You've got some efficiency there that we may want to calculate, right? Similarly, between the inverter and the transmission, you've got the efficiency of the motor here that we may want to characterize, right? And then we'll have the global or the system efficiencies, so from the battery to the mechanical power, right? So we'll want to characterize all these, especially, electrification engineers, they need to optimize every element, right? They need to optimize them for efficiency. They need to optimize them for range, especially the battery, right? But also for durability and for user experience. And all this requires to know accurately the electric power and to know the efficiency of the conversion from electrical to mechanical power. So that's what we're going to focus on, right? For instance, we want to display some efficiency maps for the inverter. So what's the efficiency of the inverter in various speed torque configurations? Similarly with the electric motor, and we could look at the system efficiency, right? So the efficiency is between 0 and 100%, and again, it's a map. The x and y axes are the engine speed and the engine torque. But to fully understand and quantify all this, we first need to measure some raw data. By data, I mean voltage, current, torque, speed, etc., and all this in the time domain, right? So my next slide is about the data collection with the eDrive Power Analyzer. So its name indicates that it can do some analysis as well, eDrive Power Analyzer, right? We'll come to that in a minute. But basically, the usual or typical power analyzers that produce just operating points at various speed and torque values. Here with the eDrive, we collect high-speed electrical and mechanical digitized data under the form of time series, right? So synchronously and continuously, we will record electric signals, whether it's coming from the battery, DC current and voltage, or from the inverter with the AC signals, multi-phase current and voltages, right? We'll measure the torque and speed. We've got very good torque transducers at HBM, right? So here you get a representation of one. So we can measure very accurately the torque values and the speed. And so this gets collected, recorded in perfect sync with the electric signals, right, at very high speed, very high sample rates. But we can also collect other sensors such as thermocouples, for the temperature. It can be interesting to capture the winding and the magnet temperatures and in sync with the electric and mechanical data, right, to understand what creates the heat, for instance, or accelerometers, right, for NVH vibration analysis, and again relate the vibrations with the torque ripple, etc. And last but not least, we have the CAN bus that we can also record. So if you're doing to test draft cycles, right, or you do onboard measurements, you can, for instance, capture the vehicle parameters, right? So all this captured at a very high sample rate, as I said. The bandwidth is higher than 1 megahertz, and therefore it's also particularly suited for measuring transients, not only steady state, from the grid, or it could be really transient signal. It'll capture them very, very well, and that's and allows one to comply with the requirements from the World Harmonized Light Vehicle Test Cycle Standard, right? The WLTC, for instance. The accuracy is really good. And again, as I said, we get best in class sensors in HBK, especially for torque and current transducers. So let's continue with the ability for the eDrive to do some real-time analysis. So it does have real-time power calculation capabilities based on cycle detection, which is really, really good, really powerful. But it also produces a file containing all the raw digitized data and the calculated data. And the format of this file is PNRF. And the nice thing is that ENCODE GlyphWorks, the ENCODE software in general, can read the PNRF files. And this enables us to visualize the file, zoom in and out, and overlay, etc., and also process the data. So talking about processing, right? Offline, if you process the data offline, you've got less constraints compared to processing the data, real time, and therefore we can address transients and the fact that some of the signals are non-sinusoidal, or they have variable frequencies, or they have a different number of phases, right? You've got 6 phases instead of 3 or what. Being in the post-processing phase enables you to, take your time and take the right action, take the right strategy to address those issues that you can't do real time, right? So what typically we use a post-processing software for is to quantify, for instance, the influence of the harmonics on power and efficiency. As you know, the currents coming from the inverter and voltage is far from being nice sinusoids, right? So if you do the power spectrum of these signals, you'll see loads of harmonics, and if you look at the signals, they look very noisy because of all those harmonics on top of it, and this has an influence on the power and on the efficiency of the inverter. So by doing it offline, you can find a cutoff frequency, filter, and quantify the influence of those harmonics on your efficiency. You can also quantify the effects of torque ripple, since we are collecting all this data at a very high sample rate, very high bandwidth. We see the actual fluctuations, oscillations of the torque signal around a mean value, right? So we have the ability to quantify that and to see what are the effects of that downstreams in terms of acoustics, or vibration, or even durability. Another application of running analysis offline is to compare different designs. So you've got design A, design B, and you wonder which one is more efficient in given situations, or you've got your competitor's engine or system that you want to benchmark, right? So this can be very easily done offline. And last but not least, it allows you to diagnose any problem during your test, to troubleshoot, and do in-depth analysis, and that's particularly useful when running expensive, long dynamic tests, or during drive cycles. It's not easy to reproduce the test, so you can do all your what ifs and troubleshoot offline and understand what went wrong and how to optimize that. So in terms of the benefits now, it means, with the, running it in GlyphWorks in a post-processing phase, you can optimize the control of your motor, of your system. You can benchmark other motors, as we said. You can assess and optimize the battery range, since the efficiency from the DC current of the battery, from the battery to the mechanical work that's created. You can you can understand. You've got a good relationship between the current draw on the battery and how the capacity of the battery gets reduced for a given requirement in terms of mechanical work, right? And you can therefore understand better your battery range. And you can also validate any model that you could have. You can model your motor or your system. It's full of equations and maths and physics and stuff. But at some point, you need to validate it and understand if there are discrepancies. Where do they come from? Again, do what ifs and stuff. So to validate your model, having the raw signals and running it in a post-processing fashion is probably the best thing to do, right? So the main message of this slide is, with offline data processing, you get more insights out of your test data. So how do we do that? We'll use GlyphWorks, ENCODE GlyphWorks, and that's an example workflow that can be built in GlyphWorks. And let's look at it a bit closer. So here we've got input files. So those are the measurements. Here you see the current 1, 2, 3, voltage 1, 2, 3. So it's a three-phase AC current and voltage, but we have more channels in there. And the nice thing is in here you can concatenate different runs. If you've got a 1 sec run for each a combination of speed and torque, then you can combine them all to see eventually the time series of torque, how the torque power, how the power fluctuates, and to get all those nice results. So that's what I did in this screenshot, right? I concatenated them all to get a big, huge file, but for all possible speed and torque values. Then what I did here is I filtered, a low pass filtered those signals, and that was done to remove the harmonics, simply because they pollute the calculation, especially for power calculation, reactive power, apparent power. They're often skewed due to the presence of the harmonics. So what I did is I created a spectrum. I looked in the frequency domain, decided where to put my cutoff frequency, and this icon here, this algorithm here is a low pass filtering the signal. And then the low pass filtered signal goes in input of the new electric power glyph. When I say new, it's in the media release that's of GlyphWorks, of ENCODE software, that's just been out a week ago or so. So feel free to download it from our website, and you'll see this new glyph called electric power. And this one calculates power and efficiency, basically, right? And the output of this glyph are time series, basically. So you've got the AC active power, a reactive power, apparent power, you get a DC power, you've got the mechanical power, if in the input files you've got torque and speed, you get the power factor, etc. We'll cover that. We'll go more in depth with this glyph in a sec. And the nice thing is you can also display those values in an efficiency map using the surface plot, which is also a very recent glyph that we added. And by connecting it straight to the surface plot and doing a very limited amount of config in this glyph, you very quickly get to this efficiency map that you see here. Again, we'll discuss this a bit more in the next slides. So that's a typical workflow to go from raw, very highly sampled electric data and mechanical data down to the efficiency map for you to understand which are the torque and speed combinations that provide you with the best efficiency, right? So let's drill down a little bit more with the electric power glyph. So it expects in input a number of channels, typically multi-phase voltage and current signals for AC, and a DC voltage and current, and torque and speed. Now you might have just the AC channels, or just DC and torque, or it'll calculate what it can out of what you have in input, right? And what it can calculate is the active, reactive, apparent power from the end-phase AC electric signals. From that, it calculates the power factor. Then it calculates the power from the DC electric signals. It calculates the mechanical power from torque and speed signals. And it can calculate the efficiencies. So if it's got all this data that I just mentioned, it's got the active AC power and the DC power. Therefore, it can calculate the efficiency between DC and AC, in other words, the efficiency of the inverter. If it's got also the mechanical power, it can calculate the efficiency of the motor by dividing the mechanical power with the AC power. So it'll calculate, based on what it's getting input, it'll calculate all it can. And this is given as time series, as I said, and that can be very easily plugged into the surface plot glyph that we have here, and I'll discuss that in the next slide. The nice thing also is that if you want to know more about the algorithms, in the software, you've got a technical background in the glyph reference guide, in the glyph properties, in the help. You also have a worked example that helps you, wiring it and setting up the properties and stuff. It's really, really simple to use. We made it such that it's, you have literally, no questions to ask. It's just easy to set up and just run. So that's for the electric power glyph. So let's take a look at the surface plot here. So it's, as I said, it's a fairly new glyph. It's got two inputs. So far in the various screenshots I showed, we were using the time series inputs. So straight from the electric power, you can plug it into the surface plot and the time series will be displayed there. But say you have a more traditional power analyzer, which gives you just the operating points, so 3 columns, just like here, speed, torque, efficiency, for instance. Well, that's where you'd use the multi-column input. So it accepts both cases, right? Those data points don't need to be regularly spaced, and nor do they need to be in any specific order. It's just display an X, Y, Z, and do the interpolation and show you a nice top view, smooth top view colored contour plot. So in terms of colors, you can pick and choose from 8 different color palettes. So I typically show this one, the blue to yellow, but we got blue to red and, gray, shades of gray and blue, and we've got 8 different ones you can choose from. Now, if you hover the mouse over the plot, you will see the values as you move the mouse, the X, Y, and Z values. So you'll see the efficiency for that torque and that speed, which is quite useful, I guess. Within a given color, you can see, how the values vary. And it's got additional display options, like those contour lines. You can have as many as you wish. By default, you've got 10 different contour lines to help you, understand the transitions. So that's for the efficiency map. But Glyphworks has got hundreds of other glyphs, right? I think capabilities that could be useful for electrification. And one of them is, as I mentioned in a previous slide, you've got those current and voltage signals that are not sinusoidal signals, right? They've got harmonics, right? And using the frequency spectrum glyph, you can turn this data from the time domain to the frequency domain and look at the harmonics in a frequency spectrum, right? And then you can decide where to put your cutoff frequency for low pass filtering, and then you can use another dedicated glyph to low pass filter those signals, right? And then you can calculate, whatever you want, stats and power and efficiency, and you can assess again, the influence of accounting for this harmonic or not. And then, for instance, just to illustrate, the raw voltage out of the inverter can look like this signal here, quite far from being a sinusoidal signal, right? Once filtered, it looks far more like a sinusoidal signal, and you can overlay the signal, the sinusoidal, the filtered voltage with the filtered current to see the phase in a much easier fashion, more visual. So there are plenty of applications, the generic applications of generic glyphs and algorithms we have in Glyphworks to help you clean your data and extract information from your data and do what ifs. That's really important. You can how's that called? You can do sensitivity analysis, on various parameters, various aspects, and see the influence of this or that on your results. So in terms of summary, we've already reached the summary slide now. So it's important to recall that accurate electric power assessment is essential for optimizing the motor control and estimating the vehicle range, right? And using the ENCODE software, an electrification engineer can analyze the huge quantities of measured electric time series data that the eDrive can provide you. And then he can quantify the power, the efficiency, but also other stuff like NVH and durability. And finally, we can compare designs. We can compare different control strategies, and we can do, optimizations using those what ifs that are mentioned, right? So that's it in terms of the PowerPoint. Now I'm gonna show you a little demo on real data. So just as an introduction to the demo, we'll use data coming from an electric motor test rig, right? So to test data, so the test rig is made of a motor that's under test, and a motor controller, and a driving motor, some sensors, and a recorder, right? So in terms of the data acquisition, we operated the machine through various torque and speed points, so 35 combinations in total. So we got 35 records or 35 runs of 1 second each, and these will be concatenated in the post-data acquisition analysis. So that's what I'm going to show you. I'm going to concatenate those 35 runs, and I'm going to compute power efficiency, and I'll produce an efficiency map. Now, the challenge really is the high sample rate of the data. In this case, it's 500 kilohertz and over 35 seconds in total, which means we've got more than 17 million data points per channel. And since we have 10 channels in total, we've got almost 200 million data points that we're gonna process, right? So let me just share now. My ENCODE GlyphWorks. Give me just 1 sec. Here we are. Oh, sorry, I just need to reconnect. Here we are. So that's GlyphWorks with the workflow that I showed you in the PowerPoint, right? It's up in here on my screen, but it's empty now. So I've got here in the available data window the 35 runs that I mentioned, right? And the idea is I could drag one of them in here. I could drag the second one, and you'll see that it's going to concatenate them, and the third one, and the fourth one, etc., etc. So it keeps concatenating them, right? Now what I'm going to do is I'm going to remove them all and drag the whole lot, so the 35 runs, and you will see that I've got all my runs here concatenated. Now let me show you, because what we have on the screen are just the current and voltages. Maybe it's not obvious to you, but I'm telling it to you. Let me just add the torque and speed, so that it becomes clear that each run was done for a specific torque and speed value. So what is it we have here? Let me just make that bigger. So here you've got the speed and the torque, and we can't read the values, but we can easily see that we've got different values, for like the five first runs are for the same speed, but different torque, and then the speed increases in different torque, and etc. Right? So those are the current and voltages, but what we have also are the battery current and voltage, right? So we got a fair amount of data in there. So as I mentioned in the PowerPoint, the first thing we will do is a low pass filter, right? So we got different filters in here, but that doesn't matter. What matters is what is the cutoff frequency you want to use, right? So we're filtering at 10 kilohertz here in this case, low pass, to get rid of all the high frequency harmonics, and that's when we do now the electric power analysis. So if I double click on this one, I will access the properties, right? And I'm asking for everything it can calculate. And if you go on the advanced, that's where you do the mapping. What are the AC current channels? Those are the channels 1 to 3. What are the voltage channels? The AC voltage 4 to 6. We got 3 phase in this case. But if you had 6 phases, you could go like 1, 6, and 7, 12, right? Then the DC, current and voltage, the speed and torque, right? You got a few properties like the averaging frequency. It's going to calculate the power and all the values, at 100 points per second in this case here. So it's a time averaged analysis that's described in the help. So let me run this now, right? So the 200 million data points will go through the filtering and the electric power glyph, and the results will be displayed here. And there you go. So you've got the first thing we have here out of a list of output channels that you have here, right? The AC power, DC, mechanical, you've got a power factor, and you've got the efficiency in %. I decided, I configured this plot to show me that the AC power. So you've got the active in red, the apparent power in blue. They're very, very similar, and indeed the reactive in green is very low. And we've got here the DC power. So that's just an example configuration plot and then obviously, you can zoom in and change that, right? You can put cursors and really, go deeper in your understanding of the relationships between various parameters. And the same output is directed to the surface plot, and that's where I've got my nice efficiency map. So the way you'd set it up, you decide which channel goes in X. So in this case, it's going to be the shaft rotational speed. Which one goes in Y? And I picked the torque. And which goes in Z. And in this case, I've picked the DC to mechanical. So that's the system efficiency. But I could have gone for, if I'm interested in the efficiency of the inverter, I could have asked for the DC to AC efficiency. So that's the smooth version of it. You could change, a number of properties in there. You could ask for, the colors, different levels of colors, 10 levels of colors here. And you could show the isolines with smooth contour, whichever you prefer to show better what you're after, right? And in terms of the colors, indeed, I've got this list here. I've picked blue, yellow, but you could go blue, red, dark, for instance. And if you think, red, dark is rather for the low efficiency and blue is rather for the high efficiency, you can reverse that palette if you wished, right? So it's quite a flexible and powerful way of displaying efficiency maps, I think, right? And if you want to really go deeper in the analysis, if you hover your mouse over the plot, can you see the yellow window here showing me the X, Y, and Z values? So I can zoom in. If you don't know the keys to zoom in, you can always click this button here. So to zoom in, you get a left button. You just drag a rectangle, right? So I'll do this, and it's very, very handy, very, very, very useful. I think that's it, right? The other tab I've got here is just the frequency analysis. I could really quickly show you. I'll just grab one run, that'll be enough. And let me just run this one. So I've got a frequency spectrum here, and it computes, the frequency domain, spectrum for all the input channels, and so you can very easily see all the harmonics here, and therefore you can specify, you can decide where should your cutoff frequency be positioned, right? What value should you take? And once this is decided, you can apply a filter. If you follow the pipes, the filter is applied to the input data, and it's a low pass with this cutoff. And then what I did here simply is I compared. So the filtered signal with the original signal, and it does that on a channel by channel basis, right? So here, for instance, we've got the very noisy input signal and the far less noisy filtered signal, and you could go to the next channel, etc., right? So that's the way you could, easily separate the harmonics from the fundamental and just do all your analysis on the fundamental, or just get rid of one of the harmonics if you wanted to. By digital filtering, it's very easy to do sensitivity analysis on the harmonics.